we give two definitions. So let T be a linear transformation from space V to vector space W. So definition. The kernel of T is the following subspace. It's denoted ker T, and it's the set of all vectors in vector space V such that T of V is equal to the zero vector. So the kernel of a transformation is a set of all vectors that are transformed into a zero vector. And we have a second definition. The image of T is, denoted Im_T, and it's the set of all vectors of the form T of V, where V runs over the whole vector space V. So what we do is we take all possible inputs for our linear transformation and collect all possible outputs. And this collection of outputs is called the image of the transformation. Now let us look at examples. So the first example is, let's consider, so let P be a transformation from R2 to R2, which is an orthogonal projection to x-axis. So this means the following, that if we have any vector u, then what we do is we drop the perpendicular to the x-axis, and P of u is the vector on x-axis, which is the projection of the vector u. Now, algebraically, this can also be written as P transforms the vector xy to the vector x0. Right? So the vector x0 has 0 y coordinate, and so it's a vector on the x-axis. Now let us determine what are the kernel and the image for this linear transformation. Well, for the kernel, we're looking for all vectors that project to 0. So this means that so P of that vector V must be a 0 vector. Well, which vectors project to a 0 vector? Well, it's clear that all vectors that are on y-axis will project to the 0 vector. Well, for example, P of 0y, right? So this is a vector on y-axis. So it has 0x coordinate. According to our formula, so this projection will be 0, 0. And so what we see is that every vector of the form 0y projects to a 0 vector. So this tells us that the kernel of this projection is the set of vectors of the form 0y, where y runs over real numbers. Let us determine what's the image of this linear operator. So here, what we should do is we should take all possible vectors on the plane in R2 and then apply the projection operators to them. When we apply the projection operator, so the image of every vector is on x-axis. And clearly, all vectors on x-axis can be obtained as images of some other vectors under this projection operator. And so this tells us that the image of this operator P consists of vectors x0, where x runs over real numbers. So what we see here is that the kernel of this projection operator is the y-axis, and the image of the projection operator is the x-axis. In our next example, let's consider the linear operator of differentiation that acts on the space of polynomials with values in the space of polynomials. Right, so we apply differentiation to each polynomial. Now, again, let's determine what is the kernel of this operator and what is the image. Now, what's the kernel of D? So this is the set of polynomials in R of x such that the derivative of this polynomial is equal to the zero polynomial. Now, we know which functions have a constant zero derivative. So from calculus, we know that these are only constant functions. So this tells us that the kernel of differentiation operator is the set of, constant functions. Now, how about the image? So for the image of differentiation operator, so we take all images of all possible inputs. So this means that this is going to be the set of all possible derivatives of all possible polynomials. So f of x runs over R of x. Now, what can we say about this set? So can we express any polynomial as a derivative of another polynomial? And from calculus, we know that the answer to this is positive, that each polynomial has an antiderivative, which is also a polynomial. So this means that every polynomial may be represented as a derivative of something. And so this tells us that this set is actually the set of all polynomials. So this tells us that the image of the differentiation operator is R of x. For our next example, let us consider a modification of the previous one. So let's still consider differentiation operator, but now we change the spaces on which it operates. And so we say let V be the space of quadratic polynomials. So V is the set of polynomials ax squared plus bx plus c, where a, b, and c run over real numbers. And now we apply differentiation operators only to polynomials in V and consider values also in the same space V, right? So D applied to a polynomial f is equal to f prime. So we take derivative. So let us see what is the kernel and the image of this operator in this setting. So kernel of D now is the set of polynomials now in the space V such that the D of f, which is f prime, is equal to 0. And we can see that still the answer is the set of constant polynomials. So this is the set of polynomials c times 1, where c runs over real numbers. Now, what about the image of D? So now we take all quadratic polynomials and differentiate them. When we differentiate a quadratic polynomial, what we can get is only a polynomial of degree at most 1. And so what we see is that the image of D is going to be the set of polynomials of the form bx plus c, where b and c run over real numbers. So here, clearly, any polynomial of this form has an antiderivative in this set. So this means that, so we can write bx plus c as the image of some other polynomial. Well, we can even say it's an image of what? So it's d of b over 2 x squared plus cx, right? So any polynomial which has degree at most 1 can be written as a derivative of a quadratic polynomial. And clearly, a quadratic polynomial cannot be obtained as a derivative of a quadratic polynomial. So this means that this is the complete description of the image of this linear transformation acting between spaces V and itself. For our next example, so let's consider R alpha rotation of R2 in angle alpha counterclockwise. Now, again, so let us determine the kernel and the image of this linear transformation. So what is the kernel of R alpha? So, well, this is the set of vectors in R2 such that R alpha applied to V is a 0 vector. Now, so we are looking for vectors that become 0 vector after rotation. But we know that rotation operator preserves the length of a vector. And so this means that if a vector is rotated into a 0 vector, then this vector itself is 0. And so this tells us that the kernel of this linear transformation consists just of a 0 vector. Now, how about the image of R alpha? So that will be the set of all values R alpha of V as V runs over R2. So what we do here is we take all possible vectors in the plane and we rotate them all in this fixed angle alpha. And then we collect all possible values of this rotation. So here it's quite clear that the rotated vectors of a plane will cover again the whole plane. So this tells us that the image of this operator is the whole plane R2. So let us state the following theorem. Let T be a linear transformation from the space V to the space W. So then, two things. A, kernel of T is a subspace in V. And B, image of T is a subspace in W. Before we give the proof of this theorem, let us recall what is the definition of a subspace. So U is a subspace in V if three properties hold. 1. 0 vector belongs to U. 2. So if we have two vectors in U, so if U1 and U2 belong to U, then this tells us that their sum U1 plus U2 is also in U. And the third property, if we have a vector U in the set U and a scalar C in the field, then C times U is also in U. So this is the definition of a subspace. And we need to prove that kernel of T is a subspace in V and image of T is a subspace of W. So let us give the proof. Well, we start with part A. Now, we need to show these three things for the kernel. So we think U is kernel of T. What does it mean that 0 vector belongs to kernel of T? So by definition, so this means that T transforms 0 vector into a 0 vector, right? And vector V belongs to the kernel, right? So we can recall that V belongs to the kernel of T if and only if T of V is equal to 0. So this is the definition of the kernel. So this tells us that 0 vector belongs to the kernel if and only if T of 0 is equal to 0. But T is a linear transformation. And we know that linear transformations possess the property that they transform 0 vector into a 0 vector. And so this means that 0 vector belongs to the kernel of any transformation. Now let's look at the second property. So we need to show the following thing, that if U1 and U2 belong to kernel of T, then their sum, U1 plus U2, also belongs to kernel of T. Now, let us use the definition of the kernel of T. So let us spell this out. So equivalently, so the fact that U1 and U2 belong to kernel of T, so by definition of the kernel, means that T of U1 is equal to 0 and T of U2 is equal to 0. And what we need to show that T of U1 plus U2 is equal to 0. So this is what it means for U1 plus U2 to belong to the kernel of T. But here we use the fact that T is linear. So T is a linear transformation. So this means that one of the properties of a linear transformation, that T of U1 plus U2 is equal to T of U1 plus T of U2. But here we're assuming that T of U1 is 0 and T of U2 is 0 because we're assuming that these two vectors belong to the kernel of T. And so this becomes 0 plus 0, which is 0. And so this shows that if we assume that T of U1 is 0 and T of U2 is 0, then T of U1 plus U2 is also 0. So which shows the second property of a subspace for the kernel of T. Now let us look at property 3 for the kernel. So what we need to show here is the following, that if U belongs to kernel of T and C belongs to F, then we need to show that C times U belongs to kernel of T. Now, how do we prove that A implies B? So we say, let us assume A and use this information to derive B. So we say, assume U belongs to kernel of T and C belongs to F. So then, by definition of the kernel, we have that T of U is equal to 0. And since T is linear, so this tells us that T of C times U is equal to C times T of U. So this is one of the properties of a linear transformation. But we assume that U is in the kernel, so T of U is 0. So we have C times 0 vector, but this is a 0 vector. And what we see is that transformation T transforms CU into a 0 vector. So this implies that CU belongs to the kernel of T. And so here we make this assumption that U belongs to the kernel of T and C is a scalar, and we prove that C times U also belongs to the kernel of T. So this established this fact, and we proved the three properties of a subspace for the kernel of T, and so we conclude, conclusion is that kernel of T is a subspace in V. Now let us prove part B, so that the image of T is a subspace in W. So we recall what is image of T. So image of T is a collection of all vectors of the form T of V as V runs over the space V. So to prove that it is a subspace, we need to establish these three properties. So first, the property is that 0 belongs to image of T. So what does it mean? So this means that 0 vector is an image of some vector in V. But we know that this is true because T of a 0 vector is equal to 0 vector. So this means that the 0 vector is the image of something in V. And so this implies that 0 vector belongs to the image of T. And this establishes the first property of a subspace. Now let us look at the second property. So here we need to show that if U1 and U2 belongs to the image of T, then U1 plus U2 also belongs to the image of T. So again, to prove that A implies B, we assume A and prove B. So we say that assume that U1 and U2 belong to the image of T. So what does it mean? So this means that each of these vectors may be written as T of something else. So then there exist vectors V1 and V2 in V such that U1 is equal to T of V1 and U2 is equal to T of V2. So this is what it means for the vector to be in the image of T. So it means that it has a pre-image in our vector space V. But then consider T of V1 plus V2. So since T is linear, we know that this is T of V1 plus T of V2. And this is equal to T of V1 is U1 plus U2. So this tells us that U1 plus U2 is T of something, right? So this means that this vector has a pre-image in the space V. And so then this implies that U1 plus U2 is in the image of T, right? So because we were able to write this vector as T of something. And finally, I leave property 3 for you to check as an exercise. Next, we want to find the matrix interpretation of the kernel and image. Let A be an m by n matrix with entries in the field F, and let T be a transformation, linear transformation from Fn to Fm, which is given by this matrix multiplication. So such that T applied to vector V is defined as the product of A with the vector V. So we just take this matrix and we multiply it by a vector. So if our vector from Fn and we multiply it by m by n matrix, the result will be a vector in Fm. And so this will define a linear transformation. So here we see that if we are given a linear transformation from Fn to Fm, we can find its matrix. And if we have a matrix, then it defines a linear transformation. Let us see what is the kernel and the image of T in terms of the matrix A. So by definition, so kernel of T is the set of vectors V in Fn such that A times V is equal to a zero vector. But so this is the set of vectors that are transformed into a zero vector. In other words, so this is the set of solutions of a homogeneous system of linear equations with matrix A. And so this is called the null space of A. So we see that in this interpretation, the kernel of a linear transformation is just the null space of this matrix. So it's a solution set of a homogeneous system with matrix A. And so we already know how to determine it. So this means that in this setting, we can find what is, say, a basis of the kernel of T. Now, what about the image of T? So the image of T is the set of all images under these transformations. So this means that we take all possible vectors A times V, where V runs over Fn. And we can write this vector as a column vector S1, S2, up to Sn. So what we do is to construct image of T, we take all possible vectors from Fn and multiply them by the given matrix. And we collect all results. And so this collection of all possible results of this product of a matrix with this vector is called the image of T. In order to understand the structure of this set, we should use the vector interpretation of the product of a matrix times a vector. So we know that this set can be written, so if V is written in this way, then A times V can be written as S1 times column 1 of A plus dot 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 Sn times column n of the matrix A. And so what we see is that the image of the transformation is the set of all possible linear combinations of the columns of A. And so what this tells us is that the image of T is equal to the column space of matrix A. And again, we have a procedure how to determine the column space of a matrix. So this tells us that we know how to describe the image of the transformation if we have its matrix. Let us look at dimensions of these spaces in this setting. So what we can say is that dimension of the kernel of T is the dimension of the null space of A. So this is called nullity of A. Right? And so the dimension of the image of T. So this is the dimension of the column space of A. But we know that dimension of the column space of A is called the rank of A. We had the relation between these two numbers. So we knew that if we add nullity of A plus rank of A, then the result is n, so the number of columns. Now we can rewrite this formula in terms of the kernel and the image of a linear transformation. So we obtain the following theorem. So let T be a linear transformation acting between finite dimensional vector spaces. So T acts from V into the space W. Then we have the following formula. Dimension of kernel of T plus dimension of the image of T is equal to dimension of V. So here we know that any finite dimensional vector space is isomorphic to the space Fn, where n is the dimension of that space. And so now if we take this formula and interpret it in terms of image and kernel, so the nullity of A is the dimension of the kernel of T, and rank of A is the dimension of the image of T. And this n here is the dimension of the domain of T. And in case when T acts from V into W, so this is dimension of V. And we obtain this result as a consequence of this rank nullity relation and this interpretation of kernel of T and image of T as nullity and as a column space and the null space of a matrix. So let us look at the following problem. So let T be a linear transformation from R5 to R3 defined with the matrix A by saying that T applied to vector V is the product A times a vector V, where A is this 5 by 3 matrix. Find the basis of kernel of T and image of T. According to what we said before, so kernel of T is the null space of A, and image of T is the column space of A. So to find the null space and the basis of the null space and the column space, we need to do row reduction. So to reduce this matrix, we apply the following elementary row operations. So we say that new row 2 is row 2 minus 2 times row 1, and new row 3 is row 3 minus 3 times row 1. So then we get the following matrix. So the first row is unchanged. So the second row is going to be 0, 0, 7 minus 6, that's 1, 8 minus 4, that's 0, 9 minus 10 is negative 1. And here we get 3 minus 3, that's 0, 6 minus 6, that's 0, then 10 minus 9, that's 1. We have 12 minus 12, that's 0. And 14 minus 15 is negative 1. And so then we can see that we can eliminate the last row by saying that row 3 prime is row 3 minus row 2. And we can also replace this with a 0 by saying that row 1 prime is row 1 minus 3 times row 2. Right? So it's a valid procedure to perform these two elementary rows operations together, because we are always subtracting the multiple of the same row. And so the new matrix that we get will be in reduced row echelon form, and it will be 1, 2. So here we get 0, 4, and 5 minus negative 3, that's 8. And here we have 0, 0, 1, 0, negative 1, 0, 0, 0, 0, 0. So this is the reduced row echelon form. We know that the null space of A is the solution set of the system AX is equal to 0. So this means that we need to write down the solution set for the homogeneous system with this matrix. So now, to do this, we have to identify our leading variables and our free variables. So the leading variables correspond to pivots. So these are x1 and x3. So we have x1, x3 are leading variables. And all other variables, so x2, x4, and x5, are free variables. So to write down the solution, we take free variables and assign parameters to free variables. So we say that x2 is r, x4 is s, and x5 is t. And then from these equations, now we can express leading variables. So the leading variables, it becomes, so x1 is minus 2x2, minus 4x4, minus 8x5. So we get that x1 is minus 2r, minus 4s, minus 8t. And so this equation says that x3 minus x5 is equal to 0. So x3 is equal to x5. So x3 is equal to t. So this becomes the general parametric solution. And all we have to do is we have to write it in a vector form. So in a vector form, we get that x1, x2, x3, x4, x5 is equal to, and now we can separate variables. So it's r times the vector minus 2, 1, 0, 0, 0, plus s times minus 4, 0, 0, 1, 0, and plus t times minus 8, 0, 1, 0, 1. So now we obtain the description of the solution set. So the solution set, or the null space of A, or the kernel of this transformation, is the set of linear combinations of these three vectors. And these three vectors are linearly independent. So this tells us that the kernel of this transformation is three-dimensional, and here we have a basis of the kernel of this transformation. So we write down that the basis of kernel of t is the following. So we have three vectors. So we have minus 2, 1, 0, 0, 0. The second vector is minus 4, 0, 0, 1, 0. And the third vector is minus 8, 0, 1, 0, 1. So these three vectors form a basis of the kernel of this transformation. So these vectors will all be transformed into 0 by this transformation, because if we multiply matrix A by any of these vectors, the result will be 0, because these are solution sets of AX is equal to 0. And every element of the kernel, any vector which is transformed into 0 after multiplication by matrix A, is a linear combination of these three vectors, as is seen here. Now let us determine the basis of the image of this transformation. Or we know that this is interpreted as the basis of the column space of A. So let's recall, how do we find the basis of the column space of A? So what we had the following rule, that basis of the column space of A may be constructed by taking columns of A corresponding to pivot positions in reduced row echelon form of A. So here we have the reduced row echelon form of A, and we have pivots in the first and the third column. So this tells us that the first and the third columns of the matrix A form the basis of the column space. And so we get the basis of image of T is consists of the following two vectors. So 1, 2, 3, and 3, 7, 10. So these two vectors form the basis of the image of T. Now, so this follows from the fact that we knew that elementary row operations preserve linear dependencies between columns. And when we write down reduced row echelon form, so here linear dependencies between columns become visible with the naked eye. So here we see that column number 2 is just twice column number 1. So the same is true in the original matrix. The second column is twice the first one. Column number 4 is 4 times column number 1. Again, we see that this is true. And column number 5 is 8 times column number 1 plus or minus column number 3. And so this is no longer obvious, but can be verified. And so what we see here is that in this matrix, every column is a linear combination of the first and the third columns. And so the same is true for the original matrix. So this tells us that these two columns form a basis of the column space, and because image of a transformation is the column space of a matrix, and so what we get is that this is the image, the basis of the image of T. So finally, let us verify the formula relating dimensions of the image and kernel of T. So we had the formula that dimension of image of T plus dimension of kernel of T is equal to dimension of the domain of this transformation. So in this case, what's the dimension of image of T? So here this basis has two vectors. So this is 2 plus dimension of the kernel of T. Kernel of T has 3 vectors in the basis. So this means that this dimension is equal to 3. And now we look what is the domain. So the domain is R5. And so the dimension of the domain is 5. And so we see that this formula holds in this example. So 2 plus 3 is equal to 5. Now we want to introduce our next bit of terminology and talk about injective and surjective linear transformations. Before we talk about linear transformations, let us define the concepts of injective and surjective for functions. So let f be a function from a set A into a set B. So A and B are sets here. So definition, so a function f from A to B is called surjective if every element B in the set B has a preimage under F. So this can be expressed as the following statement, that for all B in the set B, there exists an element A in the set A such that f of A is equal to B. So this means that every element in B has a preimage in A. Now, diagrammatically, so this can be drawn in the following way. So here we have set A, a set B, and so we have some function that sends elements of A to the elements of B. And so surjectivity means that for every element of the set B, there is an arrow that goes to this element from set A. So we have always a preimage for element B. There will be some element A that is being sent by F to the given element B. Next, we want to define injective functions. But here a small difficulty is that, well, it's easier to explain which functions are not injective. So a function is not injective if it will send two different elements of the set A. So we have A1 and A2 that are both sent to the same element B in the set B, right? So if we have an instance, so where two different elements are sent to the same element B, just one instance of this diagram tells us that F is not injective. So let us write it down. So definition. F from A to B is not injective if there exist elements A1, A2 in the set A such that A1 is not equal to A2, but f of A1 is equal to f of A2. And so the function is injective if there are no instances of this occurring. So we cannot have two different elements of the set A being sent to the same element of the set B. Now, in order to state it in a clean way, so let us talk about negations of statements, right? So basically, so here we have a definition of not injective. To get a definition of injective, we need to take this sentence and negate it. Well, the difficulty is that this sentence contains quantifiers. So we need to talk about negating statements with quantifiers. So let us make a detour and talk about negating statements with quantifiers. So consider a statement. For all x in R, x squared is greater or equal to 1. Now, well, clearly this statement is false, right? So this means that the negation of this statement must be true. And let us find what is the negation of the statement here. So the negation means that not for all x in R, x squared is greater or equal to 1. So what does it mean? So this means that if not for all elements in R, so it means that there exists an element x in R for which this fails, right? So we get that there exists x in R such that this statement fails. So we have that x squared is actually less than 1, right? Or, so here we get that there exists x in R such that x squared is less than 1. Now, is this a true statement? Yes, it is a true statement. So there exists an element x in R such that x squared is equal to 1. So for example, x is equal to 0. So now generalizing this is the following, that so suppose we have a statement for all x and some s of x, some formula holds, right? So this is a statement. So we're going to denote negation by this symbol here, right? So now we want to say what is the negation of the statement for all x, s of x. So, and here what we see is that when we negate a statement with a quantifier for all, we get a statement with existence quantifier. So this says that if not for all x, s of x holds, so this means that there exists an x for which s of x is fails, right? Or not s of x is true. So what we get is that negation of the statement for all x, s of x is there exists an x such that not s of x. So this is how we negate a statement with a universal quantifier. So by symmetry, if we negate this statement with existence quantifier, then we must obtain this statement with a universal quantifier. So this tells us that negation of the statement there exists x with the property p of x. So this becomes for all x, not p of x, right? So because now this says that there does not exist an x for which p of x holds. So this means that for all p of x, not p of x holds. So this is how we negate a statement with existence quantifier. Let us discuss elementary logical functions. So these are and, or, and not. Right. So here, so these logical functions are applied to statements. So we can put two statements together with an and function between them. So we can say A and B. And let us write down what are the value tables for these functions. So for the function end, so if we have A and B, so here, so we have so A and B. So we could have A could be true or false, and B could be true or false. And when we say that A and B, so this means that it's true only when both A and B are true. So this means that here we have the true value, and in all other cases we have a false value. So then the next function is A or B. And again, we're going to write down what's the value table for this. So here A could be true or false, and B could be true or false. So this says that A is true or B is true. And in mathematics, we use non-exclusive OR. So this means that it's A is true or B is true, or both A and B are true. So here we get truth value everywhere except when both A and B are false. And clearly for the function not, right? So if we have so A and not A, right? So here if A is true, then not A is false, and if A is false, then not A is true. So there is actually one more function, well, which may not be considered an elementary logical function, but nonetheless this function is used a lot so in mathematics. So this is A implies B. So A implies B. And let us talk about the value table for this function. So here A and B are two statements. A could be true or false, and B could be true or false. Now, if A is true and B is true, then A implies B is true. If A is true and B is false, then so A does not imply B, right? So if we have that A is true and B is false, so this means that this is false. It is not so obvious what values to put in the second line. And in order to help us, let's consider an example. Let's consider the following statement. For all x in R, x is greater or equal to 5 implies x squared is greater or equal to 25. Now let us think about it. Is this true or is this false? Right? So I think all of us will agree that this is a true statement. And so this is true for all real numbers x. Now let us consider a specific value for this real number. Right? So let's take x to be equal to 2. Right? So here, when x is equal to 2, so this becomes a false statement. And this becomes a false statement. Right? So, but what we said is that this must be a true statement for all x. So this means that this is also a true statement for x equals 2. And so this tells us then when A is false and B is false, then the statement A implies B is a true statement. Now let's consider another example. So let's take x to be negative 10. So in this case, if negative 10 greater or equal to 5, that's a false statement. But x squared is greater or equal to 25. So minus 10 squared is 100. So that becomes a true statement. And because we said that this must be a true statement for all x, so this tells us that the statement when false implies true is also a true statement. So this tells us that in mathematics we use the following understanding of A implies B. Right? So if A is false, then no matter what is whether B is true or not, we treat A implies B as a true statement. Comparing these value tables, we can say that A implies B is equivalent to not A or B. So we know that A or B is false only in one case, when both A and B are false. So not A or B is false only in one case, when not A is false and B is false. But not A is false means that A is true. So this means that not A or B is false only in one case, when A is true and B is false. And that's what we see exactly here. So let us talk about negating these elementary logical functions. What does it mean that we say not A and B? Saying that not A and B is true means that either A is false or B is false. So this means that this is equivalent to saying that not A is true or not B is true. And so the negation of A and B is negation of A or negation of B. So likewise, the negation of A or B. So A or B is false only in one case, when A is false and B is false. So this is the same as saying that not A is true and not B is true. And finally, the negation of not A. So the double negation disappears. So this is just equivalent to A. And lastly, we can negate the implication. So what does it mean that not A implies B? So here we say that A implies B is equivalent to not A or B. So this is not A or B. But when we negate or, we put an and negate the two things. So this is equivalent to not A and not B. And so double negation disappears. So this is equivalent to A and not B. And this says, again, that the implication fails only in one case, when A is true and B is false. And so that's what we see in this table. So that A implies B fails only when A is true and B is false. So the negation of A implies B is equivalent to saying that A and not B. Let us apply our knowledge of negations to understanding of injective functions. So here we gave a definition of what is not injective. Right? So this is the condition that defines a non-injective function. So to define an injective function, we need to negate this condition. So let us write down what's the negation. And if we negate a statement with existence quantifier, then we replace existence quantifier with the universal quantifier and negate the statement that follows. So the negation of this statement will be for all A1, A2 in A, we have the negation of A1 is not equal to A2 and f of A1 is equal to f of A2. Now let us simplify this. So here we are negating the AND statement. So to negate the AND statement, we have to negate each part of it and take an OR. So what we get is we get for all A1 and A2 in A, we have, so the negation of A1 is not equal to A2. So this means that A1 is actually equal to A2. Or we have not f of A1 is equal to f of A2. But now here we have something or not something. And we see that this can be replaced. So if we have not A or B, this can be replaced with A implies B. So this gives us a definition. So a function f from the set A to the set B is injective if, right, so now we take the negation of this for all A1 and A2 in the set A, f of A1 is equal to f of A2 implies that A1 is equal to A2. Right. So here we replaced this B or not A with A implies B. Right. And so this actually does make sense. Right. So we said that a function is not injective if there is an instance when two different elements are sent to the same. And now we say that suppose we know that if we have two elements and their images are equal, then this tells us that the elements themselves are equal. So this exactly tells us that this situation is not possible. And so this becomes the definition of an injective function. Now let us talk about surjective and injective linear transformation. So let T be from acting from V to W, so be a linear transformation. So T is surjective if, so now we use the definition of a surjective function for all vector W in the space W, there exists a vector V in the space V such that little w is T of V. So this means that every vector in W has a pre-image. But then we get the following fact. So T is surjective if and only if image of T is equal to W. So indeed, so the image of T consists of all possible images. So if the set of all possible images is W, that exactly means that every vector in W has a pre-image under T. So this means that the quality of image of T to the whole space W so is exactly the surjectivity property, right? So the linear transformation T from V to W is surjective if W is the image of this transformation. Now we state a theorem about injective linear transformations. So theorem T from V to W is injective if and only if the kernel of T is equal to the zero vector. So let us give a proof of this theorem. So here this is if and only if statement. So we have two parts. So the first part says that if T is injective, this implies that the kernel of T is a zero vector. And the second part that we need to prove is that if kernel of T is a zero vector, then this implies that T is injective. All right, so let us look at part 1. So here, when we prove A implies B, so we assume that A is true, and we are trying to prove that B is true. So we assume that T is injective. So we need to show that the kernel of T just consists of a zero vector. And we know that zero vector is always in the kernel of T, because kernel of T is a subspace. So let's consider an arbitrary vector in the kernel of T. So let V belongs to the kernel of T. So we need to show that V in fact is a zero vector. So that the only vector in the kernel of T is a zero vector. So now, what do we have? We have that T of V is equal to 0 by definition of the kernel, right? So since V belongs to the kernel of T. But we also know that T of 0 is also equal to 0, right? And now we know that V is being sent to 0 by T, and 0 is being sent to 0 by T. And so T is injective, so we have this property that if f of A1 is equal to f of A2, then A1 is equal to A2. And that's what we have exactly. So we have T of V is equal to T of 0. And then since T is injective, so that's our assumption. We assume that T is injective. So by definition of injective function, this tells us that V is equal to 0. And here this shows that the only vector that belongs to the kernel of T is the 0 vector. And so this proves that kernel of T is 0. And so assuming that T is injective, we were able to show that the kernel of T is consists of just a 0 vector. Let us look at the second part of this theorem. So here we assume that kernel of T consists of just a 0 vector. So we need to show that T is injective. And so here is a definition of injectivity. So let's rewrite it in the notations with linear transformations. So we need to show that for all V1 and V2 in V, if T of V1 is equal to T of V2, then this would imply, and this is what we need to show, that V1 is equal to V2. Proving that A implies B amounts to assuming that A holds and showing that B holds. So what we're going to do is, so now we assume that V1 and V2 are in V such that T of V1 is equal to T of V2. So we need to show that V1 is equal to V2. So how do we do this? So we take this equality and move everything to one side. So then we have T of V1 minus T of V2 is equal to 0. But then, so since T is linear, so this tells us that T of V1 minus V2 is equal to 0. But, so that says that V1 minus V2 belongs to the kernel of T because it's sent by t to a zero vector. So this tells us that v1 minus v2 belongs to the kernel of t. But what is our assumption about the kernel? Our assumption is that the kernel consists just of zero vector. And so this is just a zero vector. And of course, if v1 minus v2 is in the set, so this means that v1 minus v2 is equal to the zero vector, which implies that v1 is in fact equal to v2. And that's exactly what we had to show. And so this proves the second part of this theorem. So we assume that the kernel of t consists of a zero vector, and we showed that t is injective. So that t of v1 is equal to t of v2 implies that v1 is equal to v2. Now I want to finish this lecture with a question for you. So here is a question. Let t be a linear transformation from fn to fm given, so be a linear transformation given by matrix A. Matrix A. So this means that t of v is equal to A times v. And the question is, how is surjectivity and injectivity of t related to reduced row echelon form of A? So in other words, suppose we know what is the reduced row echelon form of A. So which features of the reduced row echelon form of A do we need to look at to make conclusions about surjectivity and injectivity of this transformation?